Greetings everybody. Today we are going to see isomerism in coordination complex. So we have learned about geometrical isomerism in the previous class. Today we will see about isomerism. First is optical isomers. Optical isomers are mirror images that cannot be superimposed on each other. For example, consider this molecule. This is a coordination compound with cobalt as the central metal atom and methane 1,3 diamines the three ligands. If we place a mirror between this, we can say that one, the first is the mirror image of the second. Place a mirror and draw the image that is real. Or in other words, take a molecule and take the coordination number and flip it. And the product that obtained is the mirror image of that first form. Here, two types of isomers are there. One is known as the dextro isomer, the other is lever. And by flipping it, and if we take the second molecule and if we try to place it above the first molecule, we can see that they are not superimposable. One here is about this. If we try to place the second lever isomer on top of texture whatever, we will get something like that, something of this. Yeah, the second molecule will be like this again. So it means they are not superimposable. They are not coming exactly on top of each other. Such isomers are known as optical isomers. They are also known as enantiomers. And these kind of molecules that cannot be superimposed are also called as chiral. Two forms are there: dextro, represented by D, and levo, represented by N. And this designation is given based on the direction in which these molecules rotate the plane of polarized light in a polarimeter. If this molecule rotates the plane of polarized light towards the right, they are denoted as D or dextro. And if this molecule is rotating the plane of polarized light to the left, they are denoted as L or levo. And mainly, this optical isomer is the most common in octahedral complexes having diadentate ligands. You may be remembering what is diadentate. Diadentate means a single ligand is used for coordinating to the metal using two points. For example, here En, that is ethylene, ethane 1,3 diamine or ethylene diamine, that is commonly known as the structure as following. Here, what happens? This N, not as a nitrogen, can form a coordinate bond with the met. Such ligands are known as diadentate ligands. So, this optical isomerism is very common in octahedral complex having this kind of diadentate ligands. This is another example for optical isomerism. Here, 6 form of PtCl2En is an optically active form, because if we take one in the molecule and we try to place this above the first, we can see that they are not superimposable. They cannot be placed exactly at the same position. So this case. But in the case of trans, it's not like that. For example, trans is like this. Structure of trans, PtCl2 En twice is like this. And if we place a mirror, the mirror image is exactly similar. So if we try to place it above the first original molecule, we can see that they are exactly superimposed on each other. So this kind of molecule are not enantiomer, are not showing optical isomers. Another kind of isomerism that we have seen of coordination form of linkage isomerism. Name suggests it is something related to linkage, the link of ligand to the metal. So these are common for ambidentate ligands. What is ambidentate? Ambidentate means a ligand is such that at one point the ligand has two coordination points like N, C, S. Two points are there. This nitrogen can be coordinated to the metal, and the sulfur can also be coordinated to the metal. So at the time, only one is used for coordinating. If nitrogen is used for coordinating, then sulfur will not be used. They will not form a didentate or multidentate ligand. If at a time only one atom is used for ligand formation. If N is used, S is not used, and if S is used for ligand formation, then N will not be used. Such ligands are known as ambidentate ligand. Simple example is thiocyanate link, that is NCS. This can bind through nitrogen as well as sulfur. So these are isomers. These are known as linkage isomers because the group that is used as ligand is same, but the linking atom is different. So metal coordinated to thiocyanate using nitrogen is an isomer. Metal coordinated to the thiocyanate via sulfur is another isomer. These two are linkage isomers. Another example is the nitro group. Nitro group is a amino ligand which can use either oxygen or nitrogen for forming the ligand. For example, in this complex, there is a nitro group. Two colored isomers are there. Here, the difference in color is physical properties occurring because of the isomerism, linkage isomerism. If the complex is red color, that means the linkage is through oxygen. If it is in yellow form, the nitro ligand is linked through the nitrogen. These are the examples of linkage isomers. Thiocyanate and nitro are used for some classic examples for ligands that are showing this kind of isomerism. So coming to the next isomerism, that is coordination isomerism. That means ligand interchange is happening. So this is occurring in complexes where both the cationic as well as anionic part is a coordination entity. Example, consider here. Here, cobalt NH3 6 times is the cationic part and chromium part is the anionic part, in which the here 6 NH3 ligands are bound to cobalt 3 plus and 6 Cn minus ligands are bound to Cr 3 plus. This is an isomer of a coordination isomer of this compound here, where chromium will become the cationic central metal atom. Here, the interchange of ligand is happening. If chromium is bound to NH3 and cobalt is bound to Cn minus. So these two are coordination isomers. Difference is the ligands are interchanged between the two metal atoms in certain complexes where both the cationic and anionic part are coordination entities. Now coming to ionization isomerism. This form of isomerism arises when there is a counter ion in a complex salt and it can form a ligand with the metal. For example, here in the case the counter ion is bromide, Br minus. This Br can form a coordinate bond with the cobalt. At the same time, this sulfate group can leave and function as a counter ion. So this complex CO H3 5 times SO4 Pr, and this are ionization isomers. When they ionize, they are giving different ions. Because if we ionize this, we'll get Br minus and this complex cationic part. And if we ionize this, we are getting SO4 2 minus, and the complex part does this. So difference is observed when ionization is happening. Now coming to other type of isomerism, that is solvate isomerism. Solvation means the solvent in which the complex is dissolved is playing a role in this isomerism. This is also known as hydrate isomerism. If the water is the solvent, so solvent then form coordinate bond with the metal. This type of isomerism occurs. Solvate isomerism, and if water is the solvent, it is known as hydrate isomerism. Thus, is also similar to ionization isomerism because after ionization, the ions and counter ions are different for both the isomers. Solvate isomers' difference is that their solvent molecule is the solvent molecule can go and attach with the metal ion or coordinated with the metal ion, or it can be present as a free solvent molecule in the lattice of the complex. Example is aqua complex of chromium. This Cr H2O 6 times and close the complex part, and chloride 3 chloride ions are the counter ions, and it is violet color. And solvate isomer is here the solvent. If you take the solvent water, solvate isomer is like this: Cr H2O 5 times. One H2O molecule is leaving the coordination sphere. At the same time, one Cl minus is coming into it. So we will get this complex as the solvate isomer. So hydrate isomer. Here the solvent is water. So we'll get hydrate isomer of this complex. The color is different. It is gray green, whereas the first one is violet in color. So with this, we are coming to a brief discussion to the end of the brief description about the coordination compounds and the isomerism. I hope everything is clear for everyone. And if you have any doubts, don't hesitate to ask in the comment section. Thank you for watching. Have a good day, everyone.